Okay, I am continuing on talking about electric fields, going back to electric fields. We've done them for points, we've done them for lines, infinite lines. Now we're going to do them, as you might have guessed, for infinite planes. And this is going to be similar to something you saw a couple months ago when we were talking about planes of light and the fact that the light doesn't decrease in intensity as we move away or come closer to the plane. Same thing is going to be true for the plane of charge when it's infinite. You may say, well, you never have an infinite plane of charge. But you can assume even a small plane of charge, like a small square here, is infinite to a point for a point somewhere in the middle of it. And the assumptions we're going to make are going to be useful for us for any size planes. And it allows us to make certain approximations that work pretty well. Okay, so if you have planes of charge, we'll talk about that. We're going to start with talking about a single plane of charge. So imagine a plane of charge like this. And we're going to talk, let's say, about what's the electric field over here, and what's the electric field on this side too. And I'm going to give you, we've been using the constant that we know as the value of k for finding charge. This is a constant we've come to know and get used to probably. I should say we've used it in finding the electric field from charge. Whether the charge is a point or a line. I'm now going to give you a different constant. It's related to k. Remember, k has units of Newton meters squared per coulomb squared. That's the unit of k. I'm going to give you another constant instead that we're going to use more often now. Instead of k for planes, I'm going to give you a new constant. We're going to use this one. You're going to wonder why, and I'll try to explain it. It makes life easier, basically. It's a Greek letter, and it has a little zero after it, epsilon zero, which is known as the permittivity of free space. It's a basic constant. And this is the relationship between epsilon 0 and k. If you want to figure out what epsilon 0 is, you take 1 over 4 pi k. Now, why am I doing this? Because it eliminates some of the factors that we're going to use when calculating the electric fields associated with planes of charge. And those are used quite a bit in the circuits that we're going to be working with, going back to circuits really soon. And so, but this value is approximately, I know it to 3 sig figs, 8.85 times 10 to the minus 12th. And because k is in the denominator here, the units are the inverse of the units of those for k. Coulomb squared per Newton meter squared. That is what this constant epsilon 0 is equal to, approximately. We can use that value. All right, and you kind of have to just accept that for now. You might ask, you can keep asking why, but I'm just going to say that it makes life easier. We could use epsilon 0 for, and some books do, for point charges and line charges too. You just have an extra factor of 4 pi you have to carry around with you. And the epsilon 0 will appear in the denominator when k appears in the numerator. But for a plane, this is what the electric field strength is going to be. Electric field. And I'll go with the magnitude right now. We'll talk about the direction in a moment. But for a plane of charge, the strength of the electric field is equal to that simple. Sigma over 2 epsilon 0. Now, you know what epsilon 0 is because I just explained it to you. But you don't know yet what sigma is. But kind of an analogy to the line of charge, you might be able to ascertain that sigma refers to the charge on the plane per unit area. If it's an infinite plane, of course it's going to be an infinite amount of charge. So I have to do the same kind of thing for a plane that I did for a line. And I have to say, okay, however much charge I'm putting on the plane, I have to divide that by the area of the plane. And that's going to give me what we call the planar charge density. Planar meaning because it's on a plane. Okay, so that's what this corresponds to. The planar charge density. All right, so maybe I can do an example of this. Let's just say we have a plane, and I'm not going to make it infinite. I could make it infinite, but I'll just say it has a charge density. Let's say if I were to take a 1 by 1 square meter piece of this plane and add 2 coulombs of charge to it, or 2 microcoulombs of charge to it, then I would say that the plane has a charge density of 2 microcoulombs per meter squared. In this case, plus 2 microcoulombs per meter squared. So that's this value of sigma that I can now use. So now the electric field strength is given by 2 times 10 to the minus 6 coulombs per square meter divided by 2 times 8.85 times 10 to the minus 12. All right, so let's see if I can simplify things a little bit. I'll probably have to use a calculator. If I was in class, I'd resort to you using the calculator and me estimating it, but since I'm not in class, I'll have to do a little bit of calculation here. But I do see that these 2's cancel, at least, so that's good. And so that's going to give me that the electric field strength outside of the plane is 10 to the minus 6th divided by 8.85 times 10 to the minus 12th. Let's see what happens to the units. This is Coulomb squared per Newton meter squared. So let's see what's going to happen here as I start to cancel everything out. I'm going to have coulombs per meter squared divided by Coulomb squared per Newton meter squared. So let's see what cancels. I'll do this once, the units thing, because you'll see it all works out. So the meter squareds cancel. One of these coulombs cancels one of those coulombs. So on the bottom I have coulombs per Newton. So that means that my equation is going to be 10 to the minus 6th divided by 8.85 times 10 to the minus 12th. 1 over coulombs per Newton. And then I bring this up to here. So I have 10 to the 12th times 10 to the minus 6th divided by 8.85 newtons per coulomb. There's the units of the electric field. 10 to the 12th times 10 to the minus 6 gives me 10 to the 6th divided by 8.85. I actually don't have a calculator handy, but I know that this is going to be making it smaller by almost a factor of 10. So if I do the math, you do it on your calculator. It's going to be something like this, 10 to the 5th newtons per coulomb. And this over here is going to be a little bit over 1, something like, 1.12 or something like that. I have to check that. I'm not sure of this exact digit here, but that's close. Times 10 to the minus, approximately 1.1 times 10 to the 5th newtons per coulomb. It's going to be the value of the electric field strength outside of this plane. So this plane looks like this, keep in mind. We're going to assume that it's an infinite plane, so that it extends in all directions. And what it means is that on the right side of the plane, so if I could look at it from a side view of the plane, so the the plane will look like a line, basically, but it's really a plane. I'll kind of indicate that here. On the right-hand side, what direction do you think the electric field will be pointed anywhere in space over here? Well, it should always be pointed away from the plane because it's a positive charge. The electric field at any point x is going to be here. And matter of fact, if I drew the electric field line, it would connect all of these because the electric field lines they're always unbroken. They continue forever. They're always going to be directed to the right. They should be evenly spaced because the electric field at any position, at any point in space, whether you're close to the plane here or far from the plane here, is going to have the same value because the electric field strength does not vary with distance from the plane. If you look at this equation over here, there's no r in that equation. The electric field strength is the same everywhere on both sides of an infinite plane. So on the right-hand side, it's going to be directed in the i-hat direction, whereas on the left-hand side, the electric field is going to be directed this way. It's always directed from the positive charge. Again, the spacings on this side are going to be the same as the spacings on that side. The only difference is that on the left side, the direction of the electric field is going to be negative i-hat. So positive i-hat on the right, negative i-hat on the left. That's the direction of the electric field associated with a plane of charge. Now, for a negative plane of charge, let's say that a negative, but it had the same charge density, then the opposite would hold true, where I have the electric field directed to the plane like this, and the field strength would be equal to sigma over epsilon 0. But its direction, over 2 epsilon 0. But the direction in this case would be negative i-hat on the left-hand side and plus i-hat negative i-hat on the right-hand side and plus i-hat on the left-hand side. But the value of the electric field strength would be the same because in this case, sigma equals negative 2 microcoulombs per meter squared, but its absolute value is 2. So I'd have the same value of the electric field that I had for the positive charge here, for the negative charge over on this case. The only difference is that it's going to be pointed towards the plane on the right-hand side of the plane and on the left-hand side of the plane. So it's going to be negative i-hat on the right-hand side and plus i-hat on the left-hand side. That's when you have a single plane of charge. And actually, this should get you through most of the homework. I think there's one more question, and I'll address this again in class. But if you were to have two planes, let's say, this is going to be something like what we're going to have next week, and we're going to have for the remainder of the semester, we're going to be using a device that actually consists of two planes of charge. Now, they're not infinite because it's not possible to build a practical device that has an infinite plane of charge. But if they're really close together, which is really what happens in practice, then it's as if they're infinite pretty much because, whoops, I just erased my work. Because at most of the points in between two very closely spaced planes of charge, they're going to seem like they're very close to a plane and very far from the ends. So the ends play a very minimal role in this. So it's as if they're an infinite plane of charge. And what we'll see if we have two planes of charge, one positive, one negative, kind of like a dipole, but instead of 2 point charges, you have 2 plane charges. What you're going to see is this. Let me show you. I'll spread it out so that you can see more what's going on. The negative one here, the positive one here. Now imagine this. The negative charge is going to have electric field lines that are coming towards it on this side and towards it on this side. Maybe I should draw these in black so that you know that these are from the negative charge, so I can distinguish the two. So let's say the negative charge is this, has electric field lines coming towards it on both sides. The positive charge, on the other hand, has electric field lines that are pointed away from it. It goes on forever, by the way. So away from it. And of course, the negative charge still has field lines over here that are going towards it. And maybe you can see what's going to happen. Similar in some ways to what's happening in a dipole. Well, out here, the electric field from the negative charge and the positively charged plate are going to cancel each other out because one's going to the left, the other one's going to the right. They cancel out here. You may argue the same thing over here. They're going to cancel out over here too because those from the negative charge are going one direction, those from the positively charged plane are going in the other direction. They'll cancel out there too. However, in between, notice they reinforce. They're all pointed from the positively charged plane to the negatively charged plane. So the electric fields reinforce in between. So if the planes of charge have the same amount of charge per unit area on them, then the electric field strength inside here is going to be double what a single plane would have produced. So in between two identically charged but oppositely charged planes, one positive and one negative, but the same size charge. Let's say both have, one is plus 2 microcoulombs, the other one's minus 2 microcoulombs, for instance. The electric field strength is going to be double what it would be within one of them. So the strength of the electric field is going to be equal to 2 times sigma over 2 epsilon 0. So it's going to be equal to sigma for epsilon 0 in between two planes of charge that are oppositely charged but have the same value of charge on them. Okay, we're going to talk more about this on Thursday, but I wanted you to see this. You now have the ability to begin the homework if you choose to do so. It has been posted as of Sunday night, and see what you can do with it. And I'll see you on Thursday.